So today we're going to be introducing the thread module. If you've gotten this far, I'll assume you have some familiarity with what threads are, but as a short recap, threads allow a single process to execute multiple different parts of your program at the same time, or maybe the same part, with an asterisk though. Whether they are truly running at the same time or we get the illusion that two threads are running at the same time is more or less dependent on your operating system scheduler. Threads are cool. They allow our process, when our program turns into a process, when we start running it, to handle something like multiple requests from different users, which we will be doing in our capstone project after this course. So to get started, we're going to go ahead and spawn a thread. As you can see, I brought the thread module into scope, so I'm going to go ahead and it's pretty easy to create a new thread. All we're going to do is thread spawn, and then we're going to pass in a closure of what we want the work to be done on this new thread. We're not going to pass in any arguments right now. We're just going to say for I in 1 to not including 10, we're going to print out hi for this number, I from spawned thread. And then we're going to sleep a little bit. This is just for demonstration purposes to actually relieve the CPU of our current thread and allow it to work on another thread, preferably and hopefully our main thread. And again, our main thread is what's going to be executing within our function main, and then our secondary thread, or our spawn thread, is going to execute what's in this closure right here. So we just went ahead and printed hi, and then we're going to also call from the thread module the sleep function, and we're going to pull in duration here, and we're going to say from, oh, my computer just had an aneurysm, but we're going to say from milliseconds, and we want 1 millisecond delay, just a very short amount of time. Sleep, and then we should have a semicolon here. And in our main thread, what we're going to do is we're going to print out from 1 to 5 the same thing. And we're going to print hi from main thread. Now, before I run this, note we aren't waiting for our spawned thread to finish while our main thread is doing work. Try pausing the video and guessing what our output will be. I actually forgot to put our sleep here as well, so that we're also relieving the CPU from the main thread, and this allows our spawned thread and our main thread to more or less alternate between each other, as you can see. Although we only get up to 4 from the spawn thread, even though we have said, hey, let's loop over until 10, visually it's going to look like this. This is basically what's happening, is that in our main thread here we have called, I know, it's a very rough diagram, but it gets the job done. So we're calling thread spawn here, and this is calling our secondary thread over here, and then immediately after, our main thread is going to go ahead and print out its 1, 2, 3, 4, and our secondary thread is going to continue and print its 1, 2, 3, 4, but main is done. And after our main thread is done, it's going to clean up any other secondary thread, so it's just going to stop our secondary thread before it actually finishes printing all the way up to 9. But alas, you might say, we want our secondary thread to print up to 10. How can we make that happen? Thankfully, Rust has a way for us to join our secondary thread into our primary thread. So the way we do that is we get a thread handle that's returned anytime we call thread spawn, and this basically gives us a handle to do some control on our secondary thread. So if I say let handle equals thread.spawn, we've essentially got not a thread handle, a join handle on our second thread, and this allows our main thread to wait until the secondary thread is done running and then finish it, continue with our program. In this case, we're just going to end our main thread. So we're going to go ahead and call handle join, and then we're going to unwrap the value, because we do want to panic if we're not able to properly join our secondary thread into our primary thread. And what this is doing is kind of the same thing, but what we're doing now is we're still calling our secondary thread, and our main thread is going to more or less do its 1, 2, 3, 4 in parallel with our secondary thread here. And then our main thread's going to be done. We're going to still have this line here denoting when the main thread has done its work. And then we're going to call handle.join, right? That's what we just did over here, handle.join. And then that's going to cause our main thread to block until our secondary thread has completed its work. So we're going to see something like a zipper between 1, 2, 3, 4 from the primary, and then 1, 2, 3, 4 from our secondary thread. And then we'll see the rest of the output 5, 6, 7, 8, 9 from our secondary thread. So if I go ahead and save and do cargo run real quick, we should see something more or less like that happen. As you can see, we got a zipper from our spawned in main thread, and then we're waiting for our secondary thread to finish up its work, and that's what it's doing right here. Now we have the option of doing something kind of silly here, and that is putting our join call up here right after we've created our thread. And what this is going to do is, you could probably guess, we're going to print 1 to 10 from our secondary thread first, because we're blocked here waiting for the secondary thread to finish. And then we're going to go ahead and do our main thread work. So I'll just prove a point here. What we've essentially done is just created a glorified sequential program, right? We've called a thread, we spawned a thread here, and then as soon as we spawned it, we said, oh, just wait until that spawn thread is done with its work, and then continue our main thread work. Now let's say we want to do something like this. We want to use some data from our main thread in our secondary thread. And our first inclination may be to do something like this. Like, hey, we have a vector here, and let's print out this vector in our secondary thread here. This isn't going to work because, and I'm going to hover over the spawn function definition here and try to guess why this isn't going to work. If you started looking at the lifetime of what our closure is, as you can see here, we're taking in a generic f, and that's what our closure is. We're of a generic type f, and it should be fn once closure, but it also should have a static lifetime. So basically, we're assuming the worst case scenario here where, hey, we're not sure how long we're going to keep this thread going. It could be as long as the lifetime of the process. We're assuming the worst case scenario that this spawned thread, this closure, is going to run to the very end of our process. It's going to be the very last thing that's executed, right? And our vector here might not live as long as that. This is not a static lifetime vector. It lives for as long as the program, yes, but the compiler doesn't really know that. It doesn't check that exactly. It might make more sense to pull this out into a separate function, really. 1 second. What I've done here is I've returned a handle from this spawn worker function, but v only lives as long as it is within this this function, right? V will be dropped and be out of scope after spawn worker has finished. So we could get our handle here from spawn worker, do some stuff, but our v will be out of scope by this point, and we still might need access to v. Maybe this print line function doesn't get executed until we've already left this spawn worker, right? So maybe print line doesn't get called because a thread is executed dependent on the operating system scheduler. Maybe it doesn't get executed till down here. Maybe now it calls, here's a vector with vector v, right? And v no longer exists. So that's why we assume that when we spawn a thread, the closure is gonna live for the duration of the process itself. We touched on this a bit during the closures video, but Rust has a handy trick for us. It's the move keyword. This allows the closure to obtain full ownership of whatever value it uses. So v, if I do move vector, or should I say move closure, we have now officially taken ownership of v here. And before I do that, I'm just going to show you the cargo check message that we get if we try running it without, if I can type, moving the value's ownership into our closure. Just to make you a little bit more familiar with this, and as you can see, it suggests that we use the move keyword here, and that our borrow value v might outlive the lifetime of v itself, since we're going to assume that everything that comes within a closure should have a static lifetime. So I'm going to go ahead and put move back in here, and what we're doing now is we've officially moved ownership of v into this closure. So I can do cargo run. Here's a vector, and this is exactly why you need to be careful with multi-threaded programming, is because you might forget something like joining your secondary thread down here. What was happening before was that we're getting to here, and then our main function was done, so we never had a chance to print out our actual vector. So if I run this again, we actually get our full output as intended right there. And again, if we wanted to get rid of our move keyword here, we could put in something that is truly static. So I went ahead and declared a static array here because we can't put vectors into static memory. And I printed it out here without using the move keyword. And we're able to do this because we can guarantee that array lives for the entire lifetime of the process. So we don't have to worry about array becoming like invalid at the end of here. Array is still valid here and even at the end of main. So I'll go ahead and show that this works. Here's an array, 1, 2, 3. That's it for this video. Next up, we're going to be looking at how we can communicate between threads using channels.